Hey there, physicists. So we're going to do just a quick video to talk about two words that we know a lot about, but we want to make sure our definitions are really solid. The first one is mass, and the second one is weight. We've been talking about these words for quite a few months together, but we've got a little bit of idiosyncrasy that we need to kind of tease out. So we're going to start with mass, okay? And we've defined mass a few times throughout the year. I think some of the definitions that we've come up with in the past include things like the amount of matter or the amount of stuff an object has. Okay. Maybe the number of subatomic particles, or resistance to acceleration. Those are kind of three different ways that you might define mass. And those are all pretty great. But we actually are going to take this idea of mass and divide it into two specific types. This is one of those kind of goofy things that College Board has deemed pretty important, so we need to make sure you know them. But in terms of the big picture, this definition of mass will work pretty well. So there, like I said, are two different kinds. So the first kind of mass that we're going to define is called gravitational mass. And gravitational mass basically is comparing the force of gravity of an unknown mass to the force of gravity of a known mass. When you think about that, basically we're just trying to kind of compare and balance. And in fact, that's what we use to measure gravitational mass. We use a balance. So if you think about like those triple beam balances, you know, where they've got the pan up, oops, got the pan up here, and you put your object on that, and then you use the little sliders on the bar over here, right? So you've got this little slider and this one here, and you kind of move them back and forth. Really what you're doing, you're actually using some nice rotation, and it's using torque to try and balance these things that we know, the known masses, okay, and the known torque with the unknown, this one over here, okay? That is gravitational mass. And one of the key things that you need to know about gravitational mass is that when you're measuring gravitational mass, it's measured at rest with the object at rest, okay? And you can only measure it, maybe by definition, if the force of gravity is in play, okay? So you can't, by definition, measure gravitational mass if there is no gravitational force acting. So if you yourself are out in the middle of space with nothing anywhere near around you, gravitational mass doesn't mean anything, okay? So that's the first one. And then number two, the other kind of mass that also exists, okay, is this thing called inertial mass. And we don't use the word inertia very often, right? You've probably heard me get a little bit upset about the idea of inertia, but that's just what this is called. So we have to go with it, okay? Inertial mass is defined by Newton's second law. Newton's second law is A equals F over M, okay? Which says that if you have a mass and a force is acting on that mass, you can see the acceleration. So we can apply a known force to an object. We'll measure the object's acceleration. And if we know both the force and the acceleration, we can find the mass. M is equal to the net force divided by its acceleration, okay? Unlike gravitational mass, which is measured with the object at rest and only if Fg is acting, or we had that there, inertial mass is only measured when an object is accelerating. So there are a couple of fundamental differences between them. I'm just going to kind of recap that to make sure it makes sense. So gravitational mass, we are comparing two things, right? We're comparing one thing that we know with one that we don't. We use a balance and we measure it at rest. Whereas with inertial mass, it's defined by Newton's second law, okay? And basically, we're going to measure the force that we apply, we're going to measure its acceleration, and then we'll be able to find the mass that way. And it's measured when the object is accelerating. Now, here is the kicker, my friends. This is why we have to kind of go through this, define these, and then not get ourselves too worked up about this. Here it is, right here. For all cases, gravitational mass is equal to inertial mass. Yay! All right. The only difference is how you measure it. So again, I don't want you to get too worked up because the quantities are exactly the same, okay? The technique for measuring is where things kind of diverge, okay? So there you go, gravitational and inertial mass. The last little thing that I want to talk about quickly here is this concept of weight. We've talked about weight a little bit. We've talked about weight as it relates to mass, but I just want to make sure that we are all in agreement and that we've got it kind of got a good understanding, okay? So quick question is, what is weight? It's related to mass, right? Sure is. Weight is the force of the earth, okay, or some other object, right? It could be the sun, it could be a star, it could be whatever, we don't know. The force of the earth, we'll say in this case, on the object. Weight is a force. We know this, just want to make sure you know. How do you measure weight? You measure weight using a scale. Can be a spring scale, right, that uses Hooke's law, or it can be a scale that uses like a electrical conductivity to measure it. But really what we're doing is we're measuring the force of the earth on the object itself. And then just a friendly reminder, I think you know this, but just in case, we know that mass does not change based on the force of gravity, right? We go to the moon, we go to Mars, whatever, mass is still the same, but weight does change based on force of gravity. There you go, mass and weight.